In this work, we present blended latent diffusion, an efficient way for text-driven local editing of natural images. We get an image, a mask of the area that we want to change, and the guided text prompt. We want to output a result, such that the content inside the masked area corresponds to the text. The unmasked area remains the same as the original image, and the resulting image looks natural overall. In addition, because of the one-to-many nature of the task, we want to present many possible predictions. The previous work of blended diffusion introduced the first solution for text-driven local editing of natural images by utilizing a pre-trained diffusion model and a clip model together. However, getting a prediction of a single input, which involves batch generation and ranking, takes about 25 minutes. In addition, this method operates directly on pixels, which causes noise artifacts. Latent diffusion models suggest accelerating the diffusion process by performing it in a lower dimensional latent space. At the first stage, they train a VAE, and in the second stage, they train a diffusion model that is conditioned on the current noisy latent and the embedding of the text description. In order to convert this text-to-image model to our setting of local text-driven image editing, we suggest incorporating blended diffusion into the latent space in the following way. Given the input image, mask, and guiding text, we start by encoding the image into the latent space and noise it to a certain noise level. Then, we downsample the input mask to the dimensions of the latent space. Now, at each stage, we perform a single denoising step to get a less noisy latent. This latent is treated as the foreground and is blended with the corresponding noise level of the original latent. We perform this step k times and decode the final latent to get the result. The VAE compression is lossy, which causes severe artifacts in images whose high frequencies are important to human perception, such as images that contain texts and faces. For example, in this image, we can see that the eyes and the teeth changed significantly. Hence, if we try to edit the image with the aforementioned approach, we will get a result that changes the unmasked area. A naive solution of pixel blending results in noticeable seams, whereas Poisson image blending produces a seamless result, but it changes the original color significantly. We want a solution that is in between these results. On the one hand, it is seamless as the original edit result, and on the other hand, it preserves the background as the pixel blending. We suggest doing it via optimization. We begin with the latent optimization approach. We start with the latent code that corresponds to the edit result, and optimize it to recover the pixel blending reference. But the resulting image is over-smooth and does not preserve the background adequately. Inspired by GAN inversion literature, we suggest performing the optimization over the decoder weights, instead over the latent space. This optimization enables a near-perfect reconstruction of the unmasked area, while blending the result seamlessly. Next, we've noticed that when given a thin mask, the model struggles in generating a result that corresponds to the guiding text. We start by visualizing the diffusion process. We notice that in the early stages of the diffusion process, red warm colors are added, but they are removed quickly because of the blending during the diffusion process. We suggest starting the diffusion process with a dilated mask and shrinking it progressively throughout the diffusion process until we get the original mask size. This way, the generated concept, fire in this example, will not vanish. Our method can be applied to various use cases. For example, we can use it for adding a new object to an existing scene, or altering an existing object within a scene. It can also be used for generating novel texts. or replacing the background, and more. For more details, please read our paper.